All right, let's dive right into this. Welcome to The Explainer. Today we are going to explore what is honestly one of the most mind-bending, completely counterintuitive ideas in all of modern physics. I'm talking about quantum entanglement. We've got a really fun journey ahead of us. We're going to start with a concept that actually began as a profound philosophical physics paradox, something that literally kept some of the greatest minds in history up at night, and we'll see exactly how it evolved into the bedrock of the future's most secure communication networks. It's basically a story of how what looked like a glitch in our understanding of reality became this highly prized technological resource.
So here is our roadmap for the explainer. First up, Einstein's spooky action. Then, we'll look at hidden variables. Third, we'll get into entanglement mechanics. And finally, number 4, the quantum internet. Let's just jump right in.
Section 1. Einstein's spooky action, a philosophical paradox. Our story kicks off back in the early 20th century with one of history's absolute greatest minds, Albert Einstein. And, well, he found himself profoundly troubled by this deeply counterintuitive idea that was being proposed by his peers at the time.
Before we get into his skepticism, let's just quickly ground ourselves in the textbook science. What exactly is quantum entanglement? Well, it describes a situation where two or more particles are linked so incredibly deeply that measuring just one particle actually helps determine the outcome of measuring the other. And, here is the real kicker, this happens even when those particles are separated by vast, almost unimaginable distances. It's a behavior that just totally seems to defy the everyday rules of the universe as we know it.
Now, what's really interesting about this slide is how Einstein reacted. He famously, and honestly a bit dismissively, referred to this as spooky action at a distance. You see, he strongly believed that physics should describe a world where influences do not travel faster than light, right? And where objects possess definite properties whether or not anyone is actually looking at them. So the idea that a measurement on one particle could just instantaneously fix the state of another distant particle, that felt entirely unacceptable to him. It just completely bypassed classical mechanisms.
To really understand the conflict here, we have to contrast Einstein's view with quantum reality. Along with his collaborators, Podolsky and Rosen, Einstein formulated the famous EPR argument. He basically argued that if quantum mechanics allowed for this spooky action, well, then quantum mechanics must just be incomplete. He wanted nature to be local and realistic. He actually suspected there were unseen hidden variables, basically properties we just couldn't see yet, that were secretly predetermining the outcomes of these measurements all along. But on the flip side, the quantum reality suggested something completely different: shared states, inherent randomness, and non-locality. So yeah, this was a massive philosophical standoff.
Moving on to Section 2, Hidden Variables. Science demands an answer. Now, this philosophical debate about the true nature of reality, it couldn't just stay philosophical forever. Eventually, science demanded an actual answer.
Let's move to the timeline and see how this builds over time. In 1935, we had that EPR argument we just talked about, laying out Einstein's skepticism. But the big decisive step came in 1964, when physicist John Bell introduced Bell's theorem. This was an absolute game changer. By the late 20th century, scientists were actually conducting experimental Bell tests based on his math. And it's those exact tests that directly paved the way for the modern quantum communication networks that we are building today.
So, what Bell actually showed was that any theory based on Einstein's local hidden variables had to satisfy certain mathematical inequalities. But, and this is the huge part, quantum mechanics predicted cases where those inequalities would be violated. This is incredible because it converted a purely philosophical disagreement into a rigorously testable physical question. And guess what? Successive generations of these experimental Bell tests have repeatedly observed those violations. They definitively ruled out broad classes of Einstein's local hidden variable explanations. It turns out nature truly does permit non-classical correlations that are just way stronger than any local realist theory could ever reproduce.
All right, Section 3. Entanglement mechanics, the real physics. If hidden variables aren't the answer, then what exactly is? It's time to peel back those sci-fi tropes and look at the actual, real-world physics.
First things first, we need to understand that entangled particles are not connected by some sort of invisible physical wire or a secret signal traveling back and forth through space. No. Instead, these particles are created together in a shared quantum state. The full description of that state applies to the pair as a whole rather than to each particle independently. So they aren't two separate things trying to communicate with each other. Mathematically and physically, they are literally part of one unified system.
And this brilliantly illustrates how scientists actually observe this working across vast distances. It boils down to a three-step process.
Step 1, you make a local measurement on your particle. The outcome you get there is completely random. Step 2, you then have to compare your results with a distant observer who measured the other particle. And you do this via a normal everyday classical channel, like literally making a phone call or sending an email. Step 3, it's only when you compare those notes that you actually observe the non-classical correlations that were set by that joint quantum state.
Which brings us to a super important point. Myth busted. Pop culture really loves to tell us that entanglement means instant faster-than-light messaging, right? Well, it absolutely does not. Because the outcome of your local measurement is entirely random, you can't just choose a message and instantly send it to the other side. You still need that slower-than-light classical communication channel to compare your results. And because of this inherent randomness, Einstein's beloved theory of relativity is actually perfectly preserved in operational terms.
Phew! Let's move to Section 4, the quantum internet, unhackable networks. Now that we've cleared up how the physics actually works, let's look ahead to the future. This strange, seemingly impossible physics is actually the driving force behind the next generation of unhackable network engineering.
So the crucial point is how we actually use this stuff. Enter quantum key distribution, or QKD for short. Entanglement is now completely central to quantum communication because we can use it to distribute cryptographic keys where the security is rooted in the fundamental laws of physics itself, rather than just relying on really difficult computational math. In an entanglement-based network, if an eavesdropper tries to intercept or even just measure the quantum states, they inevitably disturb them. And that disturbance, it instantly alerts the legitimate users. It literally offers the most secure form of communication possible.
Now I want you to consider the number 79. Real-world systems add all sorts of practical complications, like photons traveling through a fiber can suffer from signal loss and noise. But recent research reported by Heriot-Watt University and their collaborators showed something pretty amazing. They demonstrated that high-dimensional entanglement can actually remain robust under substantial noise and loss. Specifically, they tested conditions equivalent to 79 kilometers of telecom fiber with significant white noise. This metric is a massive milestone. Preserving entanglement under realistic, noisy conditions is absolutely essential if we're ever going to deploy these networks in the real world.
But okay, let's ground this excitement with a quick reality check. We aren't fully there yet, for sure. A full quantum network still requires us to solve some seriously hard engineering challenges. We're talking about signal loss, decoherence, which is just the fragile quantum state breaking down over time, creating reliable photon sources, developing quantum memories to actually store the data, and building scalable repeater architectures to boost the signal across those long distances. However, the global vision for this is incredibly clear. The long-term goal is a full-blown quantum internet, where entanglement is distributed reliably across metropolitan, continental, and eventually even global distances. To actually achieve this, we're going to need a really complex, beautiful mix of terrestrial fiber systems, satellite links, and those all-important repeaters to extend the entanglement step by step without destroying its fragile quantum character. The really amazing news here is that thanks to progress in areas like high-dimensional states and loss-tolerant protocols, the barriers we are facing right now are purely technical, not conceptual. We know the physics works, we just have to engineer the tools to pull it off.
Which brings us to our conclusion. You know, Einstein's skepticism wasn't just some mistake to be easily dismissed. It was a powerful challenge that sharpened one of the absolute deepest debates in the history of science. By aggressively questioning whether quantum mechanics was complete, he accidentally inspired the exact theoretical and experimental work that made entanglement one of the most useful features of modern physics. What looked to him like an unacceptable paradox has literally become the working resource for secure communication. So I'll leave you with this final provocative thought. If Einstein's unacceptable paradox ultimately gave us the foundation for the ultimate secure network, how will the quantum internet rewrite our understanding of reality next? Thanks so much for joining me for this explainer, and I'll catch you next time as we continue to break down the fascinating structures of our world.